All right, so vectors. All right, so vectors have both a magnitude and a direction. That's what makes them special. So the magnitude is a number value, and the direction is the angle, I suppose. So the vectors, like from this is very basic, but just to remind us all, vector from A to B would have a distance and direction. It'd be written A, B with an arrow over it, or sometimes they refer to them. U and V is used a lot, as you may know. So if you have two vectors, for instance, such as U going this way and V going that way, and you want to add those together, it's called the vector sum. And that would be this distance here, and that'd be U plus V. So start point, end point, the most direct route, I suppose, if you think about it. So if it was the vector from A to B and B to C, so that'd be A to B, and that's a B, and that's A to C. These two added together, AB plus AC, then, plus BC, then is just A to C directly. You can see that B will disappear out of that in a way if you're adding. When you're subtracting vectors, so if you're subtracting U minus V, well, what you think about it is it's U plus minus V, so it's like the, if you write it like that, that will help us subtract vectors. That's adding and subtracting of vectors. So subtracting that would just be the opposite direction then of V. For scalar multiplication, so in other words, if U is a certain vector, 2U would just be twice that distance. So it reaches twice as far. If your scalar multiplications is just a normal multiplication of each. Okay, so that's some super basic stuff from vectors that should be well known. Moving along from that, let's talk about the scalar product, also called the dot product. Sean, my first question.
Yes.
What does the scalar product give us?
Oh, I remember. Scalar product.
What is the meaning of the number it gets?
That's not the one that's perpendicular to both of them, is it?
The one that's perpendicular to both of them.
Or is that cross product?
It's going to be a, yeah, that's cross product, yeah.
Scalar product is, I have forgotten.
Okay, yeah. We'll come to that in a sec, what it actually means. But let's look at how we do it first. So the dot product, you could probably do it from this form, but if you transfer them into column form, so this one would be 3, 2, and 1, and this thing is called column form, and you do it like that. And we want a dot product, U dot V, we're looking for, with 5 minus 4 minus 2. Okay, so dot product is multiply the I, the J, and the K's and add them together. So U dot V, the dot product, is, for this one, 3 times 5 plus 2 times minus 4, times minus 4, plus 1 times minus 2. And that, 15 minus 8 minus 2, and that gives us an answer of 5. So what is the meaning of this number 5? Well, the answer to that is it doesn't mean very much. It's not. Meaning is questionable. It is just used in other formulas. So it is used most to find angles. So it is part of the angle formulation process, I suppose. If it is greater than 0, what does that tell us about the angle between U and V?
If it's greater than 0?
Yeah. Remember what that tells us?
Don't remember, no.
All right. So it's based off the fact that cos theta, which is one of our formulas, is U dot W times the two magnitudes. Why did I use W? V, I'm using U and V. U magnitude and V magnitude. So if you think about it, if this number up here is positive, the magnitude is always going to be positive.
Yep.
If this number is positive, that means the cos of theta is positive, which means it's in the first quadrant or it's an acute angle. If this angle is negative, that means it would be an obtuse angle or more than 90 degrees, I suppose. And if it's 0, then what?
If it's 0, then it's 90 degrees. They're perpendicular.
Yeah, exactly. So if the dot product is greater than 0, that means it's an acute angle. If it equals 0, that means it's 90 degrees. And if the dot product is less than 0, so a negative number, it is more than 90, it's an obtuse angle. Okay, so that concept is important, that we know the number itself doesn't tell you anything about a magnitude, direction, or anything like that, really, but it just helps you form the angle.
Yeah.
And therefore, often questions will just say something, the dot product is equal to 0, and then you need to know straight away if the dot product equals 0, that's a 90-degree angle. Those two are perpendicular. Okay. So with this, we might as well use the dot product to find the angle between these two vectors. So cos theta would be then u dot v, which you already got as 5. Magnitude, Tamara, remind me how to get the magnitude of u. Can you remember?
I kind of remember square root of something, right?
Yes, the square root. The square root of wasn't it 3 squared plus 2 squared plus 1 squared? Square rooted. So the magnitude, if we're taking notes, the magnitude of u would be 3 squared plus 2 squared plus 1 squared square rooted. So it's like the distance, or sorry, it's like Pythagoras' theorem a little bit. So that'll be, in this case, I've worked it out already, as I think that's square root 14. So that's u, the magnitude of u, and magnitude of v then is square root 45. And if you use your calculator, you can get theta then to be 78.5 degrees, and we use degrees in vectors. Okay, and that is the first thing. So scalar product, and I suppose we did angle between two three-dimensional vectors. Okay, let's move along. Let's talk about the vector equation of a line. Okay, so if we are given 2 points in a three-dimensional space, we can find the equation of the line between them. Well, it's a vector equation because it's going through 3 dimensions. It is similar to our coordinate geometry. If you think about it, y is equal to mx plus c is coordinate geometry, where m is, of course, the gradient, and c is the y-intercept. For the vector equation of a line, it's r is equal to a plus tb. What that is, or something like that. It's very similar. Where a is the, what's a? Sean, do you remember what a is?
Is a one? No, I don't remember.
That's the position vector. So a point that line will pass through. So it would be either A or B in this case, if we're given A and B.
Okay.
And the for B then is the direction vector. So where it's going after that. Yeah. Okay, so hopefully that makes sense. It's quite a similar formula in a way. So in order to find, this, we need, I suppose, these as vectors. First of all, at the moment they're points, but we can turn them into vectors by just finding their vector from the origin. So the vector from the origin here is the distance from or the direction from O to A, which is going to be 1, 2, 3. Hopefully that makes sense. And OB then is 5, 4, minus 2. So it's easy to get that. But we also, so we need a position vector, and that is 2 options for our position vector. We know that the line goes through both those points, so they can both be position vectors. So probably 1, 2, 3 I would use. It's the easy one. So then I just need the direction vector. So that would be getting, how would it get from here to here? Okay, so often AB, I just think of it as jumps. How from 1 to 5, what's the jump there? And it's an increase of 4. From 2 to 4, what's the jump there? It's an increase of 2. And from 3 to minus 2, the jump is decreasing of 5. So that's the direction vector between A and B. Now, there is a formula for that where you do subtraction and stuff, but probably not necessary. Okay, and then once we have a direction vector and we have 2 position vectors which form the equation, or is equal to the position vector, which I'll take 1, 2, 3, I could take either of them, plus t times some multiple times of 4 to a negative 5. So often in these questions, if it moves on from this vector equation, the t would be literally a time. So after how much time, where the vector be? And you can use this vector as long as it's on this path and on this line. You can use that that t. You can guess that t after 2 seconds or whatever, and that's if its time is that parameter. All right, this can be turned into parametric equations, so you can look at each individual direction or axes, I suppose, if you need to, and they're quite often used to solve for t or something like that, find the time. And we know that or then, the first parametric equation is or plus 4t, the second, so that's the first line, or plus 1 plus 4 times t, and so on. And so the next one would be or is equal to 2 plus 2t, and or is equal to 3.
Do we not write like x is equal to 1 plus 4t and y is equal to...
Sorry, I'm writing x. Yes, you're right. Yeah, x, y, z, yes. My apologies. Yeah, x, y, z. If you're turning it into parametrics, 2 plus 2t, and z is 3 minus 5t. And then if you know there's, if you have another set of direction vectors, often you can let that, where they meet, and you can let t is equal to, and there's an s from the other one, and you let the x's, the parametric equation equal each other and stuff like that. Okay. Let's talk about where 2 lines do meet then, which will show you how to do what I just said. So that's the intersection of 2 lines, 2 vector lines. So hopefully this is just jogging your memory and just this is the, I suppose, the simpler end of vectors. But there's not a lot to vectors. We'll bring it up to planes, and then after planes, it's just a combination of all these things. These are your skills.
Yeah.
Let's say we've line 1 is equal to, or is equal to minus 2, minus 1, 0 is the example that I have written, plus t is 3, 2, 1, so different, 3, 2, don't write it as a fraction. And line 2 is, or is equal to 1, minus 1, and 8, and s then would be 1, so minus 2, so or t and s are usually used as the multipliers of the scalar for the direction vector. Okay, first of all, do they actually intersect? And what's it called if they do not intersect?
They're parallel if they don't intersect.
Not necessarily.
Oh wait, no, because this is 3 dimensions now. Yeah.
Yeah. So there is a word.
Non-intersecting.
Skew.
Skew.
Yeah.
I remember that word. Yep.
So if they miss each other, which they can because now 3-dimensional space, they are called skew. Okay. So there will be no point of intersection. So let's solve it, and hopefully there is a point of intersection. Let's do that. Can you remember how to do it? Just said it on the other thing.
We equate each of we use the parametric ones and equate them.
Yes. So x is equal to minus 2 plus 3t from here, and x. So we're trying to find that point x, y, z that they will equal each other. So we let the parametrics equal each other. So for the x parametric, minus 2 plus 3t from the first line, it should be at some stage equal to 1 plus s, and so on. So I'll do the second one as well. Minus 1 plus 2t is equal to minus 1 plus 2s. And the last one is the 0 plus t, so 0 plus 1t is equal to 8 minus 2s. Okay, and then there's 3 equations, 2 unknowns, so it's actually quite a simple solution. So once you've got valid solutions, s is 3, I think, and t is 2. I won't do that for you, I presume you can do that. And therefore, you can find the position then. That's not the position, is it? How would I find the position that they meet?
You substitute s into its equation or t into its equation, and they should give the same point.
Exactly. So if I replace 3 and 2 here, you should get the exact same point. And I think if you do, we'll just do line 2, for example. Or is equal to 1 minus 1 and 8, and plus s being 3 times now. And this is scalar multiplication, so that's an easy multiplication. And 2 minus 2. So you can just do this in your head. 1 plus 3 times 1. I'm going to write the answer over here. So the point of the meet is 1 plus 3 times 1, which would be 4. Minus 1 plus 3 times 2, which would be 5. And 8 plus 3 times negative 2, which would be 8 take away 6, which is 2. So this is the position, the intersection of those 2 lines, the coordinate. That is the vector coordinate of that point. So that's how you find the intersection of 2 vector lines. You form the parametrics and let them equal to each other. Okay. Moving along. And now we're going to look at the final thing I'm going to look at today, and then we're going to do some questions, is the vector product.
That's the one that gives perpendicular to both of them, right?
Yes, so that gives something coming towards the camera or away from the camera, the perpendicular. But we'll talk about that in a second. What's the other word for vector product?
Cross product.
Cross product. Okay, so that when you have 2 vectors, let's have a little look. Let's look at how it works. A, B to be 2, 3, and 5. And AC, let's say 1, 2, and 4. So we have 2 vectors here. The cross product, or the vector product, will give us another vector that is perpendicular to both of these. And as I said, it'll either come out of the screen towards us, or it'll dive into the screen. So you won't be able to, it's very difficult to draw on a 2-dimensional plane, obviously. All right, so for the cross product, we set up a matrix, A, B, A, C, and we will write it, we do I, J, K, and I 2, 3, 5 for A, B, and 1, 2, and 4. Now there's a number of ways you can set this up. You can just line them up side by side, but I think it's easier to visualize it this way. There's a number of things. Right, so the important thing here is when you're doing I, often people forget they just add them all. The J coordinate's going to be subtracting, but we'll come to that in a second. But we'll just look at the I coordinate in a second. So I, if you want to do I think you may remember this, you kind of cross out the I column, and then you just look at the cross multiplication, so cross product of the other 2. So it'll be 3 times 4 minus 5 times 2. And that's the process that always happens. 3 times 4, take away 5 times 2. Now, always minus the J component.
Yep.
You cover the J line, and then you do the same thing.
2 times 4 minus 5 times 1.
Yes, 2 times 4 minus 5 times 1. J, and then you add the k component. And do the same thing, cover a k, and then do 2 times 2 and 3 times 1. You good tomorrow? Any questions?
Why is it minus for j and then plus for k?
It's just the rule. It's just the rule. I probably should know the answer to that. I can't remember why it's always minus, but it is just the rule. Perhaps I need to look that up. I can't remember why it is. Maybe I'll make a note of that for tomorrow. Does it make is there a logical reason just thinking about it? I presume that it's because the j vector is the one that comes out of the screen. It's the one, the third. Usually when they do it, that's the dimension that comes out of the screen, I think, when you draw it.
So that's the dimension that makes it perpendicular.
Yeah.
I guess all of them need to be together to make it perpendicular.
Yeah, but I think that might be where it's from, but I don't quote me on that. That's just my logical processing on the spot. But you know, like all good mathematicians, just learn it off. That's a joke. All right, so 2i minus 3j plus k, when you go to work those out, you will get that. So this vector, 2 minus 3, 1, will be coming out of the screen. Now there's a way of telling if it comes in or out of the screen. It's called the right-hand rule, and because I've just written right-hand rule. So you look at your AC, so it's like AC. If I go A, C, and B, so that's AC, and this is AB. And if I've drawn them and I'm going this way, if it's AB times AC, look at my right-hand rule. Do I do this again? I'm going to have to remember, I'm going to give you the wrong information. It's something like, if it goes this way, it's towards us, and if you're going this way, it's into the table. This way is towards anyway, I remember that, but I can't remember how you do it showing your thumb. And this way is away from us. There's a way because you have to turn your thumb inside to go that way. And I don't know if that makes sense. But it's called the right-hand rule. Maybe you can look it up on YouTube. I'm sure there's a YouTube video. Okay, which isn't going to be necessary to. You're not going to be able to show it because they're never going to ask you to draw a three-dimensional vector in an IB exam. So, but it's just interesting to know whether it goes away or from to us or away from us. Anyway, the cross product can also be used, besides finding this, it can be used then to find the area because it's got that perpendicularness to it. So the cross product is often used to find the area of the triangle or parallelogram made from A, B, and AC. So the area of the triangle is then just half the magnitude of AB cross product AC. So you have this, and then you use the magnitude, which we showed you earlier, and you can get the area of the triangle. Don't need to show you how to do that. And
why does that work?
Well, perhaps you can, if we think about it, because it is a multiplication.
Yeah.
So obviously the area of a triangle formed is the multiplication of a distance multiplied by the perpendicular height. This is the perpendicular.
This is the perpendicular height. Okay.
This is not just the perpendicular height. Yeah, it is. it is a combination of the two, and it is perpendicular. So therefore, it would be.
Okay.
I don't know. Can you try and visualizing that in three-dimensional space?
Visualizing 3 dimensions is hard.
Well, you live in a three-dimensional world.
I know, but I don't. I don't try to visualize vectors.
No, often not. Perhaps you can have a think about it. I don't know if I can. It's going to be very difficult for me to draw. Parallelogram then would just be the magnitude of the cross product of AB and not half of it, which should make sense if just knowing between a parallelogram and a triangle anyway. Okay.
Yeah.
Okay, so perhaps I can find a video that would visualize this better. I'm going to pause at that, and I put some easier, more straightforward questions that don't involve planes, which we look at tomorrow, on that document, which I think I linked on ManageBack, but I can link again in the chat here if you're not on it. Can you see on it? Oh, you're on it. Okay. So they're more straightforward questions. If you're looking at them now, they shouldn't take any more than 5 minutes each.
Okay.
Get those done before tomorrow, and you can ask me any questions on them tomorrow. Tomorrow, I suppose you stay on the line for a minute.
Okay.